All right, guys, looking at 10.1. 10.1, intro into chapter 10. Chapter 10 is all about circles, two-dimensional circles is what we're dealing with here. So definition of a circle is the set of all points in a plane that are equidistant from a given point, right? And you could do this with, something in a pencil, actually a compass, right? It's a given distance away from a point. You draw that the same distance away from the point, and it makes a circle. Okay, so that's the definition. The center, of course, is the center. When we write it out, we can either write it as circle P, right? We always name it based off of the center of the circle. So this is circle P, or you could use the circle with the dot in it as the label. It can't just be a circle because then it looks like OP or 0P. It's got to be the circle with the dot, so it's circle P. Okay. Other vocab stuff that we got to look at here, right? This is just our intro into circles. So there's a lot of stuff to just kind of point out definition-wise that we most of this we already know, right? We know, of course, that's the center. We know a radius is from the center to any point on the circle. Diameter is all the way through the center from one side to the other. And we have this idea of a chord, okay? If you've already done chapter 11, then you know chord of a sphere. But chord of a circle is just connecting any 2 points on the circle. And it goes through the circle. So a chord goes through the circle, any from one point to another. And if it happens to go through the diameter or through the center, that's when it's called a diameter. Okay, so that's why you see a diameter as a chord that contains the center of the circle, because it's connecting 2 points on my circle, but it is going through the center. Other things that we have that are new, this idea of a secant. A secant is a line that crosses through the circle. Okay, it crosses at 2 points. So it's a line, not a line segment. A chord was a line segment where it had endpoints on the circle. Secant is a line that goes through the circle. So we've got the arrows, it continues on forever. A tangent, and now this is not the tangent that we saw in chapter 9. This is not the trigonometry tangent. Same word, different meaning. So this is the tangent of a line, tangent of a circle, and it is a line that touches the circle exactly at 1 point. Okay, exactly at 1 point. I know it's kind of hard to draw in where it's only touching at 1 point, but a tangent is at 1 point. Think of a ball sitting on a table, right? Where that ball meets the table, that is going to be your tangent. That point of tangency is that 1 point where it touches. Okay, so tangent is the line itself. The point of tangency is the 1 point that the tangent shares with the circle. So let's make sure that we have those, we know those, have those definitions down. Part of what they're going to ask you to do is they're simply going to ask you to identify what types of lines or segments or rays or whatever we have here. So if we look at this, right, we have segment AC. Remember your labels, right? This is a segment because there's no arrows on it. This would be a ray because there is a one arrow on it. This would be a line because there's two arrows. And that's going to make a difference here, right? So if we talk about segment AC, we're looking here, that of course is a radius. Segment AB is now a diameter. Ray DE, and I think it's a ray. It doesn't matter whether it's a ray or a line or a segment in this case, because that is tangent. So tangent could be a segment, could be a ray, could be a line, could be anything, as long as it only touches at that 1 point. And then line AE, we're crossing through the figure, and it is a line, so this is a secant that goes through it. All right, so that's the basic of the lines of it. Some more definition stuff that we got to talk about though, when we talk about what are called tangent circles and concentric circles. Okay, tangent circles are circles that touch at 1 point. So circles that are tangent to each other, or they only cross at 1 point. You could have internally tangent, where one is inside the other. You could have externally tangent, where they are both outside and they touch at that 1 point. Notice they have the same line, the same tangent line at that point of tangency, whether it's here or here, right? They share that one tangent line. So those are tangent circles. We have concentric circles over here. Concentric circles are circles that share a center. So they share the center of the circle. They're two different sizes, but they share the same center. They are said to be concentric. If you take Spanish, we know CON means with, and centric means center. So with the same center, that's what we're talking about. Concentric is with the same center. We could, of course, have 2 points of intersection between circles, like a Venn diagram. This does not have a fancy name like the other ones do. Okay. All right. The line that crosses through, okay, if we look at our tangents here, a line or segment that is tangent to two different circles is called a common tangent. Okay, a common tangent there. And depending on what it looks like, we say they're either internally or externally tangent. Now, if we look at A, B, and C here, and we find our common tangents, okay, where they have in common. Well, for A, we could draw in a tangent line that is tangent here and here, right? Touches each one of those circles in one spot. That's a common tangent. This is also a common tangent. Okay, touches each of those in one spot. But we could also have internally tangent. Internally tangent, or a common internal tangent, is where it crosses between the two figures. So sometimes it's a little harder to draw, but it'd be something like that, where it touches only at one point each still. So it's still tangent, but now it's crossing in between. There would be another one here as well, like that, where it touches here and here. So we've got the purple ones, which were external tangents. The red ones were internal tangents. Now, if the circles themselves are tangent, or if they intersect, you cannot have internal tangents. There's no room for that to go in between. Well, in fact, there's one internal tangent. Sorry, there's one internal tangent here, right? But there's no space in between here. I can't draw in internal tangent lines on that. We can still have externally tangent lines, right? We still have lines on the outside here and here, lines on the outside here and here to have those external common tangents, but we can't have internal in this case. All right, moving on. Couple theorems that we have. Yep, we are getting back into theorems. Doesn't mean that we have proofs. Okay, no proofs. We're talking theorems here. And we got two that are pretty important, that are going to help us solve some problems in this section and moving forward. The first one, tangent line to a circle theorem. Not that you need to know the name. You just need to know what it says. And what it says is that when we have a tangent line and we have that point of tangency, if we draw in the radius to that point of tangency, it's always going to be perpendicular to the tangent. And this is important because wherever I draw that tangent line, there's an infinite number of tangent lines in a circle, right? It could be anywhere. But when I draw in that tangent line, if I draw in the radius connecting to it, it's going to be perpendicular every single time. Wherever that line is, right? I draw in the radius connecting it, it's going to be perpendicular. Okay. So that's what we're looking at for this one. It has to be perpendicular. And notice it's an if and only if. So what that does for us is if we have a radius and we have a line and they are perpendicular, we know for sure that this is a radius and that is a tangent line, right? Most of the time we're going to use it as, hey, this is tangent. What do we know? We know it's a right angle, and we're going to end up solving some problems based off of Pythagorean theorem and the likes of that, because we know it's a right triangle. So that's that first one. The second one, external tangent congruence theorem. This one's saying if you have a point anywhere outside the circle and you draw in the two tangent lines from that point, they are going to be congruent. Okay, so any external point you draw in your tangent lines, RS, or RS, ST have to be congruent. It's true for any point, right? I put this point in here. If I draw in the tangent lines and I connect to my points of tangency, those two are going to be congruent. If I have a point here, right? I draw in those two tangent lines. Those are going to be congruent. Wherever that external point is, you draw in the tangent lines, they're going to be congruent. So we're going to solve some problems like that. We're solving for X here, we're setting up equations. Okay, but those are the two theorems for this section that we need to know, and really what a lot of our questions are based off of. Let's take a look at some of the types of questions that we're going to see. We're going to see a type of question where it says, is ST tangent to circle P? And this is where that biconditional, that first theorem comes in. Is it tangent? Well, what do we know? If it is tangent, that means this is going to be a right angle. Well, how do I prove that this is a right angle? I use Pythagorean theorem to see if this works. 12 squared plus 35 squared equals 37 squared. And if that works, then it's a right triangle, which means that is a right angle. So that's what we would do to check that. If we use our calculator, 12 squared plus 35 squared and 37 squared, we'll see that the two sides are in fact equal, which means that it is perpendicular. Okay, so that's just Pythagorean theorem, seeing if it works. Okay. Another type of question that we're going to see here, and this one's based on the second theorem. This one's pretty straightforward. We know anytime we have an external point tangent twice to our circle, that those two tangent lines or those two segments here are going to be congruent. So we would just set 28 equals 3x plus 4. We would solve it out, make it equal to, or make it x equals something, and we get our answer. Answer there, of course, will be 8. But that's what we're going to do. Just set those equal to each other and solve it from there. Another one like that would be this one, right? We've got tangent lines, so we can set those two equal. X, of course, has to equal 3. Okay. Now, the other type of question that we need to look at, and this is probably the trickiest question in this section, is going to be this one. And this is a good question. I really like this type of question. And we're going to see it, we'll probably see it on the quiz or the test as well. You'll see it in the homework, I'm sure. Or they give us this information. Now that 50 is representing A to this point, A to the circle. And then R, of course, is our radius here and here. And what we're trying to do is we're trying to solve for the radius. Okay, we're trying to find the radius of circle C here. So we know that point B is a point of tangency. So if this is a point of tangency, I know I have a right angle there. It has to be a right angle. Remember, a tangent line and a radius have to be perpendicular. So it's a right angle there, which means I can set up Pythagorean theorem. Now I'm going to set up Pythagorean theorem with my two legs, right? R and 80. So that's R squared plus 80 squared. And then my hypotenuse squared. My hypotenuse is not 50. My hypotenuse is this whole thing. So my hypotenuse, when I look at it, needs to be 50 plus R. It needs to be those two things added together. And just for sake of standard form, we're going to call it R plus 50 instead of 50 plus R. Either way would work. But that leaves me with this as my Pythagorean theorem. R squared plus 80 squared equals R plus 50 in parentheses squared. And then we got to solve it. The problem comes in, people try to just distribute that square, and we cannot distribute the square. Okay, if you think back to algebra, you cannot distribute that squared sign. There is a shortcut that we could do. Chances are we don't remember that shortcut. That's perfectly fine at this point. But what we need to do is we need to rewrite that. R plus 50 squared means R plus 50 times R plus 50. So as you can think, and hopefully you recognize it now, we got to FOIL that. We have to FOIL it. If you don't FOIL when it's in parentheses like that, you are going to get it wrong. You got to FOIL that side. That's first, outer, inner, last. So first is R squared, outer 50R, inner, 50R, last would be 2,500. So we can simplify that, combine those middle two, and we're looking at that on the right side. Okay, like I said, this is probably the hardest question that you're going to see, hardest type of question. So now we're solving for R. Good news is that the R squareds cancel each other out, right? The R squareds cancel each other out. I'm left with 6,400 is equal to 100R plus 2,500, and I can solve for R pretty easily. Right, subtract the 2,500. What's that going to give us? That's going to give us 39. 39. It's going to give us 3,900 is equal to 100R. Divide by 100, and we're going to get 39 as that radius. Now we could double check, right? We could take that 39, put it here, realize that this is going to be 89, and then try our Pythagorean theorem and make sure that it works. But that's what we're looking at. Okay, you've got to set it up with the parentheses. You got to FOIL it so that it's going to work there. All right, and don't forget your label on this problem. It would be 39 feet for that. All right, that is it for 10.1. Okay, a lot of vocab stuff, so make sure you got your vocab down. And then those two theorems is really where we're going to start solving equations. And we're going to get into more of these solving for X and that sort of thing as we move forward through chapter 10. So that's 10.1. Hopefully we're good. We'll move on next time.